Thank you, Kristen. Good afternoon, everybody. My name is Mona Vail. I serve on the Predictability, Predictions, and Applications Interface panel of the U.S. CLIVAR. The mission of PPAI panel is to foster improved practices in the provision, validation, and uses of climate information and forecasts through coordinated participation with the U.S. and international climate science and applications communities. We felt that the topic of scientific uncertainty is a critical one to the weather, water, and climate community. It is a topic that needs more discussion, so it was my honor and pleasure to invite a couple of experts who have been working in the field of scientific uncertainty, looking at it from various perspectives. So for this, the summer edition of Variations that focuses entirely on uncertainty, we have Judy Curry from Georgia Tech, who provides an overview of climate uncertainty and risk. We also have Adrian Wooden, who is going to talk about statistical downscaling and the uncertainty associated with it. From an application standpoint, we have two speakers who are going to talk about uncertainty as it relates to agricultural adaptation planning, and that is Chin Fei from Texas A&M University, and we have William Cheng from University of British Columbia, who is going to share his perspectives on uncertainty and fisheries management. And to conclude this webinar today, we'll be hearing from James Stone at the National Center for Atmospheric Research. James and Rebecca Moores are conducting a project or implementing a project that looks at decadal climate predictions and the associated uncertainties and how to communicate those uncertainties. So it's a nice way to round up the conversation and discussion related to scientific uncertainty. So without further ado, welcome panelists. Thank you so much for taking the time to share your thoughts with us, to compile the articles, and to be here. So Kristen, over to you.
Yeah, thank you, Mona. I think we can turn this right over to Judith. Please go ahead.
Hello, everyone. I'd like to thank Kristen and Mona for putting this together and for inviting me to participate. As scientists, we focus on the knowledge frontier where doubt and uncertainty are inherent. With regards to models, we're mainly concerned about whether a model helps us learn about how the systems work. However, in context of the science policy interface, uncertainty matters. There's a growing need for more constructive approaches to accounting for uncertainty in climate change as related to policy making, what may happen in the future, and what actions might be appropriate now. Over the past 15 years, I've been addressing the issue of uncertainty in climate models and how we should reason about climate change. Some of you may recognize the uncertainty monster. My article on climate uncertainty and risk integrates perspectives from climate modeling, philosophy of science, and decision-making under uncertainty. The objective is to explore the kinds of evidence and reasoning that can help inform decision makers as to whether and how they should use climate models for different applications. The characterization of uncertainty presented in my paper focuses on model predictions for an intrinsically probabilistic system. The categorization discriminates among two dimensions of uncertainty: location and level of uncertainty. The location of uncertainty refers to where the uncertainty manifests itself within the model complex. Framing and context addresses boundaries of the model system. Model structure uncertainty relates to uncertainty about the conceptual modeling of the physical system, including selection of subsystems to include. Model technical uncertainty includes solution approximation and numerical errors. Then we have input uncertainty, parameter uncertainty, model outcome uncertainty, and uncertainty quantification error, which is associated with the Monte Carlo sampling used in the error quantification procedure. Most of the attention is paid to parameter uncertainty and model outcome uncertainty. However, I've argued that the locations that deserve the greatest reflection are framing and model structure uncertainty, which are not quantifiable uncertainties. The level of uncertainty relates to where the model outcome uncertainty ranks in the spectrum between complete certainty and total ignorance. Complete certainty implies deterministic knowledge. Statistical uncertainty implies that precise decision-relevant probability statements can be provided. Under scenario uncertainty, a range of plausible outcomes are enumerated, but there's a weak basis for ranking them in terms of likelihood. Under deep uncertainty, the scientific basis for developing outcomes is weak, such as when future outcomes lie outside the realm of regular or quantifiable expectations. And finally, total ignorance is the deepest level of uncertainty, where we do not even know that we do not know. These are the unknown unknowns. So how does characterizing uncertainty interface with the policymaking process? In the context of decision-making, risk is the probability that some undesirable event will occur and is often described as a combination, that the probability and the corresponding consequence of the event. Decision-making is straightforward for situations where we have precise probabilities of potential outcomes. However, decision-making is much more challenging for conditions of scenario and deep uncertainty. In my paper, I argued that if the policy-making challenge is defined in context of the response of climate to future greenhouse gas emissions, then the uncertainty level is characterized as scenario uncertainty. Scenario uncertainty arises not only from uncertainty in future emissions, but also from uncertainty in the equilibrium sensitivity to carbon dioxide. Despite the fact that we know a range of values within which the equilibrium climate sensitivity is likely to fall, we do not have grounds for associating a specific probability distribution for the equilibrium climate sensitivity. And if the policy-making challenge is defined in the context of actual evolution of the 21st century climate, such as for vulnerability and impact assessments, then the uncertainty level increases to deep uncertainty. Apart from the issue of unknown future greenhouse gas emissions, we have very little basis for developing future scenarios of solar variation, volcanic eruptions, and long-term internal variability. The likelihood of unanticipated outcomes or surprises needs to be acknowledged. The IPCC Fourth Assessment Report provided the following conclusion. There is considerable confidence that climate models provide credible quantitative estimates of future climate change, particularly at continental scales and above. Is this level of confidence in climate model projections justified? Climate models have been evaluated by assessing how well results fit data and how well they agree with other models or model versions, and also their coherence with background knowledge. A broader perspective on this issue is provided by recent scholarship on the epistemology of simulation, including how simulation models are confirmed. Philosopher of science Wendy Parker has argued that agreement with other models does not objectively increase confidence in simulations of future climate change. This raises questions as to what we're actually accomplishing with the plethora of MIPS. Assessments of empirical accuracy are fraught with challenges: inadequacy of data, selection of variables to confirm and on which time and space scales, a vast and multidimensional parameter space to be explored, among other issues. Known climate model error may be too pervasive to allow climate model confirmation to be of use. Wendy Parker proposes a shift in approach from confirming climate models to confirming their adequacy for purpose. Now, assessing the adequacy for purpose of predicting future climate is arguably impossible. Empirical accuracy may be largely due to tuning rather than to the model's structural form. Further, the model may lack representations of processes and feedbacks that would significantly influence future climate change. Given these concerns, philosopher of science Joel Katsev argues that useful climate model assessment should aim to demonstrate that the simulations describe real possibilities. A simulation is taken to be a real possibility if its realization is compatible with our background knowledge. Scenario falsification assesses whether background knowledge excludes the realization of the simulated scenario over the target period. The possibilistic view regards the spread of an ensemble as a range of outcomes that cannot be ruled out. Existing climate models, however, do not allow exploration of all possibilities that are compatible with our background knowledge. Some of these unexplored possibilities may turn out to be real ones. There's value in scientific speculation on policy-relevant aspects of plausible high-impact scenarios, even though we can neither model them realistically nor provide a precise estimate of their probability. The worst-case scenario is judged to be the most extreme scenario that cannot be falsified as impossible based upon our background knowledge. The scientific community involved in predicting future sea level rise has expended considerable effort in articulating the worst-case scenario. Also, the recent paper on hothouse Earth provides another example of generating a worst-case scenario. So how can policymakers deal with conditions of deep uncertainty? I really like this diagram that I borrowed from one of the other papers. I've argued that we're dealing with high uncertainty in context of the 21st century climate in the realm where scenario planning or adaptive management are appropriate strategies. However, the decision analytic framework that's being used for many policy decisions is optimal control. The precision of cost-benefit analyses, such as the social cost of carbon, is illusory and fraught with assumption and value judgments. Policies optimized for a likely future may fail in the face of surprise. For situations of deep uncertainty, scenario planning and adaptive management are appropriate decision analytic frameworks. The following statements summarize the main take-home points I've tried to make in this paper. Scientists should avoid the attrition of uncertainty in the face of an inappropriate demand for certainty from policymakers. Encouraging overconfidence in the realism of current climate model simulations can lead to questionable policy outcomes. And finally, I question whether the path we are currently on for developing and evaluating climate models is the best use of resources for supporting policymaking. I described some new challenges for climate scientists to develop a broader range of future scenarios, including worst-case scenarios and regional scenarios. Thank you. I look forward to your questions.
Thanks, Judith. Do we have any questions? Looks like we have a question from Dan. 1 second. Dan, you with us?
Yeah, I'm here.
Please go ahead, ask your question.
Hi, Judith. That was a great discussion, or a great presentation. I think it hits on a lot of things that PPAI has been discussing over the last couple of years as well. So I appreciate that very much. Do you have a small question? Do you have a reference for that last matrix that you showed there, the 2x2?
Oh, I spotted it on the tweet. Mona, maybe you know it. Somebody tweeted that figure. The U.S. CLIVAR office tweeted the figure.
Okay.
Yeah, that's from William Chung, who we'll hear later from today, and he was talking about fisheries. So he put that in his article, and he may show it again with some more context regarding fisheries management. Yeah.
I do. I love that image.
that's really nice, and I think I think there's been a growing set of use of scenario development and adaptive management in looking at dealing with uncertainty for future projections, which is really encouraging to see. But on a large scale, I think I like that because I feel like you're kind of hitting the nail on the head for the way this tends to be viewed. So thank you.
Thanks, Dan. Real quick, William, are you planning to show that figure later, or should we talk a little bit about it now?
Yes, I will show that figure again, and I think that's a really good link to Judy's presentation, because then I can talk more about a specific context in fisheries for discussing that framework presented in that figure. So by the way, the figure was originally published in a paper led by Gary Peterson from Stockholm Resilience Center. It's Peterson 2003, and the reference is in my article.
Great, thank you. Peter, did you have a question for us? Please go ahead. Peter, you may want to check the mute on your computer.
Okay, I see a written question.
Yes, hi. Can you guys hear me now?
We can hear you. Please go ahead, Peter.
Okay, sorry. This is just I think I probably asked this on Twitter before. So Dr. Curry has graciously entertained some of my more, I guess, critical questions about this sort of framing of the Parker you can't trust agreement. You can't trust model agreement as evidence sort of model realism, and it seems to me that there's some tension between criticizing the proliferation of MIPS and sort of also the kind of relying on Parker's warning about relying on model agreement, because it would seem like the proliferation of MIPS, especially in terms of process MIPS or paleoclimate MIPS, actually does exactly what Parker would seem to suggest we need in terms of feeling more confident in sort of the realism of modeling.
I speak to the early days of MIPS when I was an active participant, and this was model intercomparison with little input from any empirical evaluation. And it helped identify bugs in some of the outlier models. Okay, so it was useful from that perspective. But at some point, the models started agreeing with each other, and they would just, more and more case studies and things like that. For process modeling with very careful evaluation against observations, that is useful. But for the global climate models, I think the MIPS are sort of like a diminishing return at this point. Again, when there's a major element of empirical evaluation, I mean, that is obviously worthwhile, but just straightforward model intercomparison, I would agree with Parker that we've reached the point of diminishing returns on that for the global climate models.
But aren't a lot of these, like a lot of the same GCMs that are used for the future scenario output, they're the same models that we're using for stuff like Pliocene modeling intercomparison or even deeper time MIPS, and that seems like there's a little tension between kind of saying, well, we've got all this uncertainty because the models are too tuned to the observational record, and we don't want to have this proliferation of MIPS, and yet those MIPS are giving us this sort of out-of-sample check against overly tuning.
Again, taking a step back, I think the fundamental issues are at the structural uncertainty and the framing uncertainty levels. And by continuing to focus on what I would say the more MIP kind of approach, we're sort of neglecting those. I mean, in the early days, I think the MIPS were useful, but I think it's diminishing concerns. I mean, that's just my opinion. I throw that out there as, I'm more concerned about the lack of focus on structural uncertainty and framing uncertainty. That's my bigger points. I just threw the myth out there.
Thanks, Judith. I think that's a good response. And Peter, that was a great question. I think we could probably spend a lot of time talking back and forth on that, but we do have some other speakers. And we're going to real quickly, I think, Mike, you had a quick question? Or do you want to wait till the end?
I can wait till the end, but just wanted to put on the screen that we have this new working group in US CLIVAR focusing on large ensembles, and I'd be interested in hearing, and we can do this at the end, hearing thoughts on, in addition to, or instead of MIPS, future direction that we might want to consider going is a focus on these large ensembles, 50-plus members, to really tie down the uncertainty due to internal variability. Yes. Short answer, yes.
Okay. Yeah, there's been a focus on, using the computer power on reducing the resolution. Okay, but I think that computer power would be better used on larger ensembles and really starting to understand the internal variability. I totally agree with that focus.
Okay, great.
Thanks, Mike. Thanks, Judy, so much. Okay, we're going to move on to our next speaker, which is Adrian. Adrian, you're on. Please go ahead and show us your slides. Great. Adrian, is your phone on mute on your end? We can't hear you.
There we go. Is that better?
Much better. Thank you. Please go ahead.
Sorry about that. So I was trying to say thank you for inviting me to write and present. It's an honor and a pleasure. Before I dive into some of the topics in my article, which gets into some more of the major and semi-minor issues with statistical downscaling and its particular subtle processes, which I think have more influence than we realize on the uncertainty, I want to just, for those who aren't familiar, dive into what downscaling is really briefly. So in essence, the way you can think of downscaling is that it's a process of making a link between the state of some variable in a large space and the state of some variable in a much smaller space. It's one of my favorite definitions from Rasmus Benestad. But in essence, what downscaling tries to do is to reintroduce the effects of a local and regional scale climate, things like topography and proximity to coastline and their physical impacts upon temperature and precipitation in the climate that can at best be approximated by global climate model parameterization schemes. In this particular example, we can see on the left-hand side that in temperature, the gradients that we would expect with the Appalachians are not present in the global climate model simulation and its coarse resolution, whereas under a downscaling simulation, they would be reintroduced and become much more evident, along with other contrasts in temperature that are much more evident also in the Rockies. So just as one example of what downscaling attempts to do. Downscaling's work begins after the global climate modeling work ends. Regardless of what kind of downscaling is being done, all the issues with the GCMs are, all the issues and information from the GCMs are the primary input to doing downscaling. Statistical downscaling is one such form of downscaling. It's a fairly popular approach for doing it, as I've lost track at 30 plus different papers and different ways to do statistical downscaling, but its premise is about the same between each type of downscaling that exists. You have historical GCM simulation and historical observations. You train a statistical relationship between the two, and that relationship is used to downscale the GCM to get an estimate of observations. In the historical period, we have our comparison that gives us a measure of skill. But then from there, you also have that relationship applied to future GCM projection, and that gives us a downscaled estimate of future observations. So inherently, statistical downscaling actually has two inputs, all of the output from the global climate model simulations, but also whatever historical observations are used to build said relationship. Aside from that, though, there are some really subtle and simple processes that most people would ignore, and maybe this is a little into the, pardon the euphemism, sausage making, that is statistical downscaling. But these are behind-the-scenes things that perhaps have a little bit more influence than we realize and have received very little attention in the current literature. So as I mentioned, there's two inputs to statistical downscaling, but there's also lots of subtle processes, and this is only a partial list. There's actually quite a few more that I could add to this. Subtle, but perhaps more important than we realize. So in some cases, there's interpolation that's required as part of the downscaling process. So how is this done when you're talking about daily precipitation, for instance, that is discontinuous in nature? How is that done for that? Or doing data transformations, or having a minimum sample size requirement, or even defining at the end of downscaling, what is a wet day? You may define that as 1 millimeter. Somebody else may define that as 1/4 of a millimeter with trace precipitation. The two that I talked about mostly in my article as examples of some of these kinds of subtle processes are better known as trace adjustments and tail adjustments. But for this whole list, when we go into the literature, there's actually very little mention of these with respect to downscaling itself and what it means for the output product and the uncertainty associated at the very end of the particular process. And so I have to ask the question, what if these little things matter more to the uncertainty of the downscale projections than we realize that they do? To look at this, I chose to use some synthetic data just to be able to eliminate some variables and have it focus solely on the difference between tail adjustments and trace adjustments. But I have this slide here just to make the point that I did not pull this synthetic data out of thin air. It is very much constrained to observation data and GCM data from the CMIP5 archive that is driven by RCP 8.5 in here with historical and future periods involved. For this just example to illustrate the potential involved, I focused also on two particular locations here in Arkansas and New Mexico. But regardless, with what you're going to see and to follow, the GCM data remain the same, the observations remain the same involved regardless. The only variations that I make with these little short experiments is to vary the tail adjustment and the trace adjustment, such little things, but perhaps more influential than we realized. The other thing to know here is the downscaling technique itself I chose remained exactly the same, and while simple as quantum mapping is, it's actually really illustrative, I think, for the point that I was trying to make. So trace adjustments, of course, why in the world do we need a trace adjustment at all? GCMs do have a tendency to overestimate low rain rate frequency, as shown by this particular figure from Pendergrass and Hartman's 2014 paper. You can actually see here with the CMIP5 ensemble, here the multi-model mean and the confidence bands, that it tends to overestimate the frequency of these low rain rate events. But this also leads to an overestimate of the number of rain days. This is sometimes also called a drizzle bias, but these trace adjustments in statistical downscaling are meant to help correct this particular feature that we see here. That said, as I mentioned in the literature, the trace adjustments used for statistical downscaling, depending upon who does their downscaling, receive very little mention and have never had the intercomparison to assess which is the highest skill involved, and also how much uncertainty is involved for things of comparable skill. And that's a short example of what I tried to do with this synthetic data involved. So what you're looking at with these is, in here is historical GCM, future GCM, and our three different trace adjustments applied with, again, the same downscaling, the same GCM involved. And these are projected values for the change in the number of days of rainfall in a region, which is something, of course, a trace would be designed to correct, is to look at, okay, we need to have the right number of days with rain involved with these things. As I mentioned, though, before, the trace adjustment is applied before downscaling, but you can still define what a wet day is after downscaling, hence the reason we have three different bars in here for just saying a wet day is anything greater than 0 versus something that is greater than or equal to a millimeter per day is a wet day. So for me, I chose with this to focus on what is a little bit more typical for weather station observations and what we would consider a wet day, in that it's anything greater than or equal to a trace. What is then the projected change in the number of days with rainfall, just varying the trace adjustment involved in this and not the downscaling technique or the global model involved. A subtle feature, but this is actually pretty wide range of variability when we think of it, with it being a 25-day range in here for just something so small as that. But the question I still am left with, okay, which is the correct trace adjustment to use? What is the highest skill involved? This is, again, something the literature provides at this point very little guidance on. In the same vein with trace adjustments, there's also the idea of a tail adjustment. And for me, this issue is best described with an example that's connected with quantile mapping, though. Quantile mapping is not the only downscaling technique where this becomes an issue. Normally, the first process of a quantile mapping relationship is to take a relationship here between the future GCM projection and its historical GCM simulation in that relationship. And this works all well and good so long as the future GCM value is within the same bounds of the distribution for the historical GCM value. But when we transition to a point location where the future GCM simulation goes beyond the bounds of the historical, there's suddenly nothing there for it to map to in that historical relationship. And therefore, what tends to happen, at least in the case with quantile mapping and a few other downscaling techniques that are statistical, this is where these relationships statistically break down at the extremes and become much less robust to work with, and where tail adjustments are implemented to help estimate extremes. But again, these are actually very limited, and in the case of some downscaling techniques, they prescribe their own for such. I think a good example actually is the CDFT package in R for that choice of downscaling technique. They have their own method that they've already prescribed in that particular downscaling software. But of course, which one? Because again, with the literature at this point, we haven't actually taken the time to explore what matters with each of these, which has the highest skill, and what's the variability involved if there's comparable skill. Looking at that same synthetic data in Arkansas, but this time varying the tail adjustment involved here, we can start to see in this cumulative distribution function at the end of the distribution where the tail adjustment starts to cause differences between the results of downscaling in this. And in some of these with the very far extreme values, I believe this is roughly 450 millimeters to 600 millimeters per day, which both are very high values, but that is quite a spread there between them, again, with this particular synthetic data. Knowing that for planning, though, this particular kind of thing of looking at a cumulative distribution function is not necessarily the most meaningful, asking more of a question like, what's the change of the annual maximum one-day rainfall from these particular kinds of simulations? What is the range there? And that's something that is pretty well known from the Clindex archive. In this case, what we have is roughly a spread of the projected change, mind you, of roughly 44 millimeters per year for this particular climatology. Whether or not this matters, that's where I get to the pragmatic and to asking the if question. Does a range like this really matter when we're starting to look at these things? And is this also something that we could reduce as a source of uncertainty? Precipitation, though, is not the only thing you can focus on, because tail adjustments also come into play with temperature. In this particular case, if we're looking again with these same three tail adjustments, but this temperature data in New Mexico, what we can see here with this is the tail adjustments again start to spread out the results of the downscaling once you get past the point where the tail adjustment is invoked in here. This particular location, the observation data didn't have in its historical period any days where the temperature was over 95 degrees Fahrenheit. And so someone may be wanting to ask in a future climate for planning in that particular region, which is part of the Gila National Forest, what does something like this mean for the climatology, the annual number of days the high temperature is greater than 95? And in this case, we find something a little bit more with this synthetic data in a very simple experiment. Is something on the order of 2 weeks of spread here in between. Does this matter from the ecosystem side of things, but also from the climate modeling side? Okay, again, the question, what is the highest skill for this? What can we reduce? And what is something in the uncertainty here that we could reduce in this particular kind of structure? The point of everything that I did here was absolutely not to say which subtle process is the best, quite frankly, because there was nowhere near enough time. It was out of the scope to do that, given the number of downscaling techniques that exist and the number of possible ways that you could approach doing some of these particular really subtle features. I have to ask my big question, of course, as I've been kind of hinting at all the way through here, is do these little things matter? These are really subtle details, and parroting off of what Dr. Curry said, this is not really well explored from the downscaling side of things, and even though it's an added modeling process on top of the modeling processes that are done for global climate modeling, we tend not to explore these things. for me, who have done downscaling and continues to do downscaling, I tend to say yes, because these are things that we can then try to characterize and work on reducing, finding the appropriate processes and statistical relationships that we could use. There's also a more pragmatic reason that I'm concerned about these kinds of little things, and that's because we're looking now in the literature and seeing more of a modeling chain that develops. You have the global climate modeling involved, we have downscaling involved, but then the next step that tends to come after that is the desire to use downscaled climate projections in a hydrology model, for instance, as with this example, which is projected river flows for a basin in Georgia compared to USGS historical stream gauges. The concern I have with this, of course, is there's some very highly nonlinear relationships there between climate and hydrology, or agriculture, or ecosystems, or fisheries, any number of different things in here. So with a little change and a really highly nonlinear relationship, do these suddenly become much more important as we characterize the uncertainty associated, but also try to translate it down the modeling chain to what it means at the end for some kinds of projections like these of stream flow. So I could talk plenty more on this, and I welcome the discussion that we can have today, and you're welcome to contact me with my email here. For now, I'd like to leave you all with some open questions that I talked about in my article, but thank you for the time, and thank you for the invitation to write and present. It's an honor and a pleasure, and if we have time now for questions, we can talk now, or we can talk more later.
Great. Thanks, Adrienne. Any quick questions? Looks like we got one from Dan. Please go ahead.
Thanks. That was a nice presentation. I guess one other issue that I guess I'd like to hear your thoughts on and progress in our field on is the stationarity assumption for statistical downscaling, and then I guess in a similar vein, that assumption for physical or dynamical downscaling, which given Judith's talk a moment ago, if you could comment on the stationary assumption in our set of dynamical downscaling models.
Mm-hmm. As it happens through some of the other work that I do here at the South Central Climate Adaptation Science Center, I do some work with NOAA's Geophysical Fluid Dynamics Lab, and they have a team there that is actually examining the stationarity assumption with respect to statistical downscaling. In their paper in 2016, which I think I cited really briefly right at the beginning here, they actually talked about this with respect to temperature, and that there are issues with statistical downscaling techniques and the stationary assumption breaking in here. So developing new statistical downscaling techniques with which we can improve upon that and overcome the issues of stationarity in statistical downscaling, I think, is important. I have thought a bit on the idea from the dynamic downscaling side, knowing that there's some empirical and statistical related things in some of the parameterization schemes that are involved, though I've not been as focused on that. It is concerning to me that I haven't seen a whole lot of focus on that because of all the approximations that are involved with parameterization schemes and subgrid scale processes and global models. So I would like to see more emphasis in discussing the stationarity issue in dynamic downscaling. I haven't seen it present as much as I would like in there, but somebody may correct me if I'm wrong. But statistical downscaling, that is something I'm actually working a little bit on in the stationary issue with the folks at GFDL right now.
Yeah, I think they've demonstrated the importance of using these kind of within model estimates there, and something I think that could be emphasized in our community as well.
Mm-hmm. Yeah, that's the folks there. The first paper was primarily on temperature, and I think right now our focus is on precipitation. And I can maybe spoil it a little bit here that some of the things that we've seen with precipitation, I really haven't seen a downscaling technique done with precipitation yet that doesn't violate the stationarity assumption just yet in one form or another. So spoiler alert with that one, but working on that particular aspect right now.
Great. Thanks, Dan. Thanks, Adrienne. I think we're going to go ahead and move on to our next speaker here. Cheng, are you with us?
Yes.
Hi, please go ahead. Thank you.
All right. So first of all, thank you for the invitation. And Dr. McCall today is traveling, so he can't be here. I will present the paper. So in our paper, we majorly address the uncertainty, the adaptation planning for agriculture. We first discussed the uncertainties in agriculture and then discuss how shall we considering the uncertainties in adaptation planning. So as we all know, by the end, by around 2050, the global average temperature will increase about 1 degree. That will raise the inevitable for agriculture to adapt. So the first uncertainty came from the technological progress. After the Green Revolution, there is a very high growth rate of the agriculture productivity due to the technological progress. So, for example, the corn yield now is about 4 times, 6 times of it was in 1950s, but the input is only about 2.5 times greater. But some researchers also show that the growth rate is slowing down, and we may and also found like the investment to agriculture R&D are slowing down. So we may think there will be a large uncertainty in the agriculture productivity due to the technological progress. The second uncertainty came from the demand growth. Based on the current projection of UN by the end of this century, we have agriculture should produce about 25 to 75% more food to guarantee the food security in the world. But also due to the income increase, the meat demand will increase, and there are some other uncertainties for the agriculture demand. For example, like the U.S. Ethanol policies suddenly increased the corn demand in the U.S. and globally. The third one came from the climate change. So there is a lot of uncertainties in climate change, and also it raises the uncertainties in agriculture. Next is the practical efficiency. Due to the changes of the precipitation patterns, the farmers may need to apply more pesticides to get the same efficiency. The water effects comes from both the supply side and the demand side. So due to climate change, the evapotranspiration and the soil moisture may changes and then raises the demand of the water demand of the crops. And also a research of Dr. Riddle found that the groundwater availability in the agricultural regions goes down, which raises uncertainty of the water supply as well. And under climate change, the frequency of the extreme events goes down. So we all know like the heat waves could kill the cattle, and the hurricanes and hails may diminish the agriculture production like crops and also livestock. So if the frequency of the extreme events increase, we may have a larger challenge for the agriculture productivity. Also, currently, we use international trade to guarantee the food security in some countries. Also, the climate change varies across regions. The international trade may contribute more to guarantee the food security, but if there are some like negative effects to the international trade, we raise the uncertainties in agriculture productivity and also the food security in some countries. The rainfall and other extreme events changes raises the challenges for the agriculture infrastructures. For example, like for now, the dam may be designed for 100-year flood, but later when the flood scale increased, we have to adjust the infrastructure to guarantee to prevent the flood effect. And also we have the uncertainties in simulating all of the effects we discussed above. We don't have a very perfect model to simulate all of the effects, and also we will have uncertainties in modeling the agriculture production. And then we discussed the uncertainties from the time scale. So some adaptation planning will have a very long time horizontal. Then during the time of implement the adaptation strategies, there will have more uncertainties, and the climate change during this time horizontal will influence the functions and performance of the infrastructures. Also, we discussed the adaptation strategies could be implemented by individual or be implemented by public, but some of the adaptations will be implemented needs the cooperating of the stakeholders. When we communicate with the stakeholders, we may find like there might be some uncertainties for the incentive of the stakeholders and also the intent of the stakeholder participation and the time to achieve the implementation. And then we discussed the next slide. We then discussed the uncertainties in the adaptation planning. So as discussed by IPCC, we must realize that the stakeholders have different performance orientations and understanding of climate change. So we may use varieties of tools to address the scope, complexity, and uncertainty of the adaptation plannings to the stakeholders. And next, we have to considering the evaluation of the adaptation possibilities. So there are already some fundings from like UNFCCC, for example, the Green Climate Funds. They already support the agricultural adaptation strategies. But when we do the evaluation for the agricultural adaptation project, we have to considering the additionality, performance, permanence, maladaptation, uncertainties, and transaction cost for the adaptation planning. For example, the additionality means we should consider like these adaptation strategy must be additional to what currently existing, or say must be additional to like the planning the farmers or other stakeholders could already take by themselves, don't need any public support. And for the other example is the maladaptation. That means the adaptation strategy could benefit one group but may worsen the situation for another group. That's the damage to the other group should be considered in the evaluation. And then we can take some non-regret strategies to reduce the risk, and uncertainties in adaptation. So the non-regret strategies may include like purchasing crop insurance, building irrigation infrastructures, but also we should know that this kind of strategy may have very low efficiency. The strategy effectiveness may be easily to be diminished by climate change. We have to monitoring and adjusting the adaptation planning during the implement. That could reduce the cumulative uncertainties and adapt the plan so it could be more suitable, and we could make the adaptation strategies reversible and flexible at the initial stage. For example, if we want to build a very large dam, if we make it very reversible and flexible at the initial stage, it will be more easier and cheaper to adjust it if the flood scale increased. And we could reduce the asset fixed time horizon. That means we could choose, if we have the option, we could choose the adaptation strategies with shorter time scale that could be less expensive and easier to reduce the uncertainties during the time horizon. And the final strategy came from the mitigation side. So in some of the mitigation strategy evaluation, when there is a lot of uncertainties, we sometimes lower the expected interval to discount the uncertainty in the planning. And now we could put this into we could put this in the adaptation side, and then that means we could also lower the confidence interval to discount the uncertainties in the adaptation project. So that's our discussion in the paper. Thank you.
Thank you very much. We can take a couple minutes here for any questions. I actually had a question, Cheng Cheng. This is Kristen. Are you familiar with any kind of case studies or localized examples where the stakeholders in the community have been involved in adaptation planning regarding agriculture and have utilized any of these no-regret strategies or anything else in their planning?
So currently I'm working on a project called Water, Food, Energy Nexus. We focus on the case study of the San Antonio, Texas region. In this region, we had some kind of water scarcity problems. And then our stakeholders include agriculture, but also include municipal and industrial and many other sectors. For now, the agriculture would be in the weak position, and they may ask to use less water because agriculture has a lower profit from water usage compared with other sectors. And then we may have stakeholder meetings, different sectors communicate with each other and try to find better strategies to guarantee the welfare for each sector, and also increase the total social welfare for the region where we have maybe severe water scarcity like that.
Great, thank you.
Okay.
Yeah, no, that sounds like interesting work. Okay, why don't we move on for the sake of time so we don't run too long and over. Thank you, Cheng Cheng. I think up next is William. Are you with us?
Yes, I am. Can you hear me?
Yes, please go ahead and share your slides with us.
Okay. Hi, can you see my slide?
Not yet.
Not yet.
Grab the share button at the top.
Sorry. Yes, I forgot to do that actually. Okay. Yes.
Great. All righty, we can see your slides now.
Yeah, thanks. So first of all, thank you very much for inviting me to contribute to the variations and speaking in this webinar. I think so far the speakers and the talks are really interesting. And particularly in my talk, I will focus on the discussions about uncertainty around fisheries management. And I think that links quite closely to the number of presentation that before me, for example, in Judith, that really set the stage in how to treat uncertainty and then the application to agriculture. So I'm bringing you to the ocean. The premise first is that the oceans is being affected by global climate change, and that ocean conditions are changing. We are seeing the ocean is warming up, it's getting more acidic, it's getting less oxygenated, sea level is rising, polar sea ice is decreasing in extent. And all these changes are projected to continue with our global system models. And these change in conditions of the oceans are affecting marine organisms, particularly for fish and invertebrates that are important for fisheries. And thus, people who are dependent on these resources will also be affected. The thing is, we are uncertain about how these changes would then have effects on fisheries and human-dependent communities. One of the challenge of understanding the future changes in fisheries and resources is that we are looking at integrated socio-ecological systems of the oceans. Particularly with climate change is altering the ocean conditions, and it affects the marine ecosystems at various levels of organizations, from the more organismal levels affecting the physiology and biology of the organisms, and then that affects the population dynamics, spatial distributions, community structure, trophic interaction, ecosystem functions. At the other side, we also have these global scale changes, such as global population growth, changes in food and commodity prices, energy price, that all affects the fishing sectors and affects their decisions of how much and where they go fishing. And of course, fisheries management also play an important role in that. And all these different changes are interconnected with one another, making projections and predictions of futures under climate change for the fisheries and how to manage that really challenging. And to give you a sense of the challenge, this is a figure of showing the global fisheries production, so global fisheries catches from the CFR's Project Catch Statistics from 1950 to 2010. It's divided by different sectors: invertebrate fisheries, finfish fisheries, and then also including aquaculture or mariculture, so farming of fish in the sea. And what our challenge is whether this the level of predictions as of now will continue in the future. We know that global fisheries catch has already peaked in around 1990s, and the catches actually has decreased in the last decades or so. Will this decrease continue, and will climate change continue to exacerbate this decrease? Or that whether other form of seafood production, such as aquaculture, would pick up some of the slack from captured fisheries and maintain or even increase seafood productions. All of these are uncertain, and that we need to use various lines of information, both quantitative modeling work, as well as some other form of information to help us gauge these potential future seafood supply under climate change. Because the seafood industry and the fisheries are interconnected to the well-being of a lot of people in the world, particularly coastal communities. So this is a global challenge to understand how seafood would change and how that would then affect the well-being of people. And as Judith really nicely laid out, there are various forms of uncertainties, and that applies to understanding and projecting future changes in oceans under climate change as well. And we have scenario uncertainty, we have various forms of uncertainty, and these scenarios and model uncertainty actually becomes more complicated compared to what just the climate models are, because now in addition to the changes in climate, we also have the changes in the ocean biogeochemistry, ocean physics, as well as the changes in fish stocks, biodiversity, and human communities. That all then interact and affects the future scenarios of changing fishing and fisheries resources. And the models become much more complicated, and the characterizations of uncertainties for the models also become much more complicated. And then there are various forms of internal variability, which are known to be big in the oceans, such as internal and interannual variability or decadal variability, such as El Nino and things like that, that really make further increase this overall envelope of uncertainty. Just to show you this chain of uncertainties and how give you a sense of how they may link to one another. This is a standard uncertainty characterizations figures for sea surface temperature from based on model projections from 1950s to the end of the 21st century. As the different color represent different form of uncertainty, while the solid line represent observations. So you see how these different form of uncertainty would emerge over different time period, as well as in different spatial scale. On the left-hand side, you have global scale where the signal is much stronger, but then once you go into the regional scale, which are much more relevant to understanding fisheries and then using the information for fisheries management, uncertainty becomes much bigger compared to the signals. And then if we add the fish projections into the whole picture, linking the uncertainty of the changes in the physical and biogeochemical condition of the oceans, and how that then modeling how we can then use those information to model fish changes in fisheries protections, the potential fisheries catches, then you see that the envelope of uncertainty actually expand. And in this case, even with the high emission scenario, it is likely that we won't, given all this uncertainty, it is difficult to see how the overall signal can emerge with when we account for all this uncertainty. And as Judy said, this is kind of a subset of uncertainty. We are ignoring some of the even bigger source of uncertainty, such as the deep uncertainty of the future changes in society, or the structural uncertainty of some of the bigger design of how we model fish and the oceans. And then there are regional differences in how this uncertainty would emerge too. This is again a similar graph like what I showed you earlier, which is the projections of fisheries catches from now to mid-century. And you see that basically just a picture of the differences in how the contributions of different forms of uncertainty actually differ in different ocean basins. And I won't go into details of each specific ocean basins, but the overall message is that it means we need to deal with the different level of uncertainties given the oceanographic conditions, as well as the kind of species that we are targeting and the fisheries that are there that may have different form of uncertainties that we need to deal with fisheries management. And then in addition to that, because fishing is still one of the biggest drivers of changes in fish stocks and fisheries. For example, with overfishing, we are actually removing more than half of the overall biomass from the oceans for the traditional fish stocks. So it means that fishing is a very dominant factor. And it also means that the way we manage fisheries also becomes a really strong factor in affecting the future changes in fishery resources and fish stocks as well. So this is an example of a study that a graduate student did for the North Sea fisheries, which highlight the difference in the way the society and the fisheries will change, actually have a much stronger effects compared to the difference between the climate models or the fish model that we used. And then on top of that, we also have the uncertainties about how we can manage unexpected changes in the oceans. So this is a study that we published very recently that highlights that there may be new fisheries that will emerge in different countries' own waters. So we use our models to project where new fish stocks will emerge because of the shift in distributions under climate change, and particularly ocean warming. And we find that in this coming century, most of the exclusive economic zones of the world oceans will see new species moving into the water. It also means that currently these species are not part of the fisheries management regime, and that these new species will pose new challenges because the existing fisheries management are not designed to cope with these new fish stocks. And this is particularly challenging if the fish stocks are shared between countries, because we know that shared fish stocks are very difficult to manage sustainably because it needs cooperation between countries. And preempting these changes are very difficult. And most of the current fisheries legislations, international fisheries agreements are not designed to cope with these new changes. So given all these uncertainties and the challenges that I just talked about in fisheries and the climate change, what are then the approaches that we can use to deal with these challenges? And this is the figure that Judith showed earlier on, which is in my article. It highlights that depending on the scale, the time frame, or the spatial scale, or the characteristics of the fisheries and the region, one may adapt or adopt different ways of managing fisheries. For example, in some cases, if there are really low uncertainty and really low controllability, it may mean that we just need to implement those no-regret management, such as setting up marine protected area, which hopefully can restore the lateral capacity of the fish stocks and ecosystems to help to absorb some of the changes that we will be seeing under climate change, as well as reducing some of the other human drivers that are known to be impacting fish stocks, so that we can again build capacities to help both the ecosystem, the fish stocks, as well as the fishing sectors to adapt to those changes. In other cases, particularly with the development of some of the more shorter-term forecasts, and in some countries where governance is really effective, then some aspect of optimal controls may be possible by doing this more implementation of fisheries management tactics that account for these more short-term but high confidence forecasts in changing fish stocks and oceans. But in most of the time, because of the high uncertainty, we will need scenario planning and adaptive management. And this is also a point that is highlighted by Judith, which I agree a lot. These are designed to these processes are designed to inform decision making and management under high uncertainty. And there are already a lot of scenarios and science that are being undertaken and developed, particularly to inform management and conservation of biodiversity and ecosystem services, including fisheries. This is a figure that I used that I obtained from one of the reports from the Intergovernmental Platform on Biodiversity and Ecosystem Services on their report for methods on scenarios and models. So basically, this outlines really nicely the different types of scenario building and how they can fit into the whole decision-making process, from using exploratory scenarios for agenda setting. So that's the gray color on the upper left-hand side of the figure, and then use those informations to actually design some policy options and policy target, so that we can then use target-seeking scenario to identify policy options that can achieve those goals. At the end, we can then also use retrospective policy evaluation scenarios to see whether these management options are effective in achieving the goals, and then obtain information so that we can then make adjustments to the policy options, and that this cycle become iterative, so that the whole process is adaptive to changes and uncertainty, and can take in new information as it comes in. So at the end, there are some challenges as progress in using scenario planning for fisheries. First of all, there are already a wide range of models and scenarios that are available, but gaps still exist, particularly capacity to use models and scenarios and the availability of knowledge and data vary between regions. Most of the time, right now, it is in developed countries where there are lots of science occurring, and such effort needs to be expanded and supported for developing countries. And this can be done by large-scale effort to develop the capacity by making information data available to support fisheries management. And for example, knowledge-based centers that bring together this information to support decision-making, to provide capacity to develop scenarios and models, and to inform policy-making, particularly in data pool situations, would be quite effective. So thank you very much.
Great. Thank you, William. We have time for a few questions. Are there any questions for him? I actually had a quick question. If no one else does, we'll see if anything else pops up. But it was a real quick question. You had a slide back there that had the global map and had kind of the fish catches on it. And it looked like the fish catch was going up in the Arctic region. Is that due to, yeah, that one. Is that increase due to kind of access from loss of sea ice or migration of fish species into the region, or a combination of both?
It's a combination of both, and this is mainly looking at the potential fisheries catches. So the main drivers for these projected changes is the warming of the oceans in the Arctic, where then some of the temperate species are able to move into some part of the Arctic oceans, and decrease in sea ice make it accessible for some of the fish stocks and potentially fisheries to exploit. And there is also some increase in potential productivity. Although there is, in some part of the Arctic Ocean, there is also actually a high uncertainty in the projected future changes in productivity, making some part of the Arctic Ocean projections actually quite uncertain too.
Okay. Great, thank you. Any quick questions? I do want to try to keep us mostly on time. That was a great presentation, William. Thank you very much. We'll take it back here to our end, and we'll wrap up. Last but definitely not least, we're going to hear from James. Sorry, James, I had you on mute. Please go ahead.
Great. Well, thank you, and thank you for the invitation to speak today. Yeah, I'm the second author on this paper, so thank you to Rebecca Morse for leading the paper, and thank you to the other co-authors. So in this overview paper, we explored the assessment and communication of uncertainty in decadal climate predictions. So a central theme here was our project UDecide. So this acronym stands for Understanding Decision Climate Interactions on Decadal Scales. So the overarching project goal is to understand the role of decadal climate prediction for water resource management. So it combines stakeholder-oriented research with statistical dynamical modeling of decadal climate. So I'll explain. So I'll start by outlining the potential value of decadal prediction. It's illustrated here by this schematic. So on the y-axis, we have some climate impact variable. This could be flood height, for example, versus time. So if you look at a climate change projection, you could linearly interpolate the climate delta indicated by the blue line. Whereas if you look at a decadal prediction in the red line, that tells you the trajectory of how you get to the future. And so if you have a, say, a water management decision that it operates on the timescale indicated by the blue shading, then the potential value of the decadal prediction is given by this green space, the difference between the projection and the prediction. So the interesting thing about predictions, or the possible use, is the potential to narrow near-term uncertainty. Okay, I'll outline our research approach. So basically, we want to identify what information is needed and what is skillful on decadal scales. So if we start with the yellow triangle on the left, this is where we want to identify the climate-related information that's needed on decadal timescales, and we do that through our stakeholder-oriented research and really to map out the climate-related decision space. On the right-hand side, we identify what's skillful in terms of decadal climate prediction, and we employ dynamical statistical methods to tell us that. So the really interesting piece happens in these green ellipses where we identify intersections between what's needed and what's skillful. But we don't stop there, that's insufficient. We then explore the characteristics of effective communication of this information while accounting for uncertainties in the predictive information. Okay, well, just an overview of what we found from our stakeholder interactions. So we interviewed folks in Colorado and interacted with water agencies in California. So let me just give a brief overview of what we found with Colorado. So we conducted interviews with the Urban Drainage Flood Control District here in the Front Range of Colorado. They're interested in urban stormwater drainage, and a key question they have is how to construct new channels and what's the balance between built versus natural channel construction. Because with natural channels, they need 2 or 3 years of no droughts and no major floods to allow the vegetation to become embedded. So if there's a decadal prediction of multi-year high flood likelihood or multi-year drought, then they'll probably resort to more concrete construction. We then interviewed Denver Water, a local water drinking utility. Their major question is, if we're in a drought, when will we come out of it? So their need is multi-year drought predictions. And then over in California, we interacted with Sonoma County Water Agency. again, one of the remits is drinking water. And their key question is, how often will organic carbon exceed a threshold at chlorination intake? So for drinking water, they have a simple chlorination system, and if organic carbon exceeds the threshold, that system fails. So they're really vulnerable to drought, and then wildfire following drought, and then a flood following the wildfire that can wash all this organic carbon into the water system. And then over at the California Department of Water Resources, again, they're interested in Central Valley drought prediction, so multi-year drought prediction. And they assess that with this 8-river index, which is a combination of stream flow at the inflow to reservoirs. And they want to know how often this index will fall below a minimum threshold. So again, we've identified a number of intersections of the needs of water managers on decadal scales. So how about where we're skillful? Well, through our interactions with the water agencies, we understood that we really need to understand processes in the system for the information to be credible. That's a key requirement for its use. So we conducted a process study to understand how decadal climate variability conditions the nature and predictability of atmospheric rivers. These are our major impact on hydrology across the western US. So we employed the model for prediction across scales, where we ran a refined global mesh down to 15 kilometers where we're interested and 60 kilometers where we're less interested. We ran an ensemble simulation of the 2016-17 winter. And we did this twice under opposite phases of the interdecadal Pacific Oscillation. So this is one of the major modes of climate variability across the Pacific. And we did that by adding an SST anomaly consistent with the positive phase of the IPO and the negative phase of the IPO. And you can see those SST anomalies on the bottom left. They look a lot like El Nino, but they also have centers of action in the mid-latitudes of opposite polarity. Okay, so let's have a look at what how the IPO affects precipitation along the west coast. Here's a difference plot, positive IPO minus negative IPO for winter precipitation. So the blue means that precipitation is reduced under positive IPO. The red means precipitation is enhanced under positive IPO, and you see this significant increase along the coastal California and Southern California. So now we're digging into the dynamics of how the jet structure is changed in response to the SSTs out across the Pacific, and how this influences wave breaking along the west coast. And in fact, when you look at actual weather systems, so here's a time series for a point location in Southern California of integrated vapor transport. So this is the product of the wind speed and water vapor integrated throughout the depths of the troposphere. And this is an indication of atmospheric river events. Now I'm just showing red lines. There's 2 ensemble members under the positive phase of IPO, and the blue are just 2 example ensemble members under the negative phase. And I'm looking at the numbers of strong events, and they are greater than 400 kilogram per meter per second, indicated by the gray dash line. And in fact, we see twice the number of strong events over Southern California in positive IPO. And the numbers of events is emerging to be a key metric for water agencies in California. So now we've started to explore processes. What about actual real-time predictions? So for this, we looked to the results of Salvi et al. 2017. They looked at a prediction that was initialized in 2015 and went out to 2024. This is an ensemble prediction. And here we're looking at the red lines are one method of bias correction. The blue line is another method of drift bias correction. The thick lines are the ensemble mean, thin lines are the members, and shading is a measure of the spread. So you can see temperature relative to normal, the prediction is for warmer, and then at the bottom, the prediction is for drier. These are for winters, over the southwest US. So we're looking at a warmer and drier future. But we know these global climate models have problems with local precipitation. So in response, we developed a statistical dynamical prediction system of US precipitation. So I'll just explain the statistical model here. So it's illustrated by this schematic here. So take the example, we want to predict spatial precipitation over Colorado, Y. We do that as a function of local predictors, in this case surface temperature, which is indicated by X. And the other predictor is a spatial pattern of ocean temperatures across the entire Pacific. So we're able to use these somewhat predictable variables to infer precipitation. So we've developed the model, and now we're in the process of applying this model to the decadal predictions I just showed in the previous slide to assess whether our statistical dynamical approach is more skillful than the raw precipitation coming from the GCM. Okay, well, on to my final slide. So now we're starting to identify intersections between what's needed and what's skillful, but as I mentioned at the start, this is not sufficient. We also want to understand the key characteristics of useful information in the way it's communicated. So to do that, we're developing prototype presentations of the real-time prediction in different frames. So we're developing a hydrologic prediction, so a streamflow prediction. We're developing a simple temperature prediction, and then a slightly more complex combined temperature precipitation prediction. And we're using these as tools to probe and advance our understanding of what an effective communication looks like. Now, the interesting thing here is illustrated by these cones of uncertainty at the bottom. So if you imagine an ensemble climate projection, so this is indicated by the big cone, we're exploring the potential role of predictions as telling you where within the larger spread we're most likely to be. So that's indicated by this smaller cone of uncertainty, the predicted range. And it may be the case that in the near term we actually lie outside of the linearly interpolated projections. And then we go beyond and explore how this is useful for water managers. So that was a quick overview of the paper, and the real purpose of our publication was to serve as a template for future studies that integrate decision-making with development of climate prediction systems. And I'll leave it there. Thank you.